Hello, everybody. I have a few announcements. One is that I've been gone for a really long time. Sorry about that. I got my master's degree in mathematics. I am now an MA in mathematics. Isn't that cool? That's what I've been doing instead of making videos. My last semester, the spring semester, was really tough because I was taking 3 real classes and my research, and I was also teaching a class as a graduate teaching assistant, and I was I had my other responsibilities as a graduate teaching assistant. So this whole thing kind of took a step back as I needed to focus on that. Still, it took maybe it took a few years off my life, but that's where I am now. And I don't know, I'm excited to get back into the analysis. All of this seems like kind of seems like baby stuff now, when at one point it was so difficult. And I guess maybe that's the sort of magic. If you spend enough time doing something, eventually you're probably going to get pretty good at it. How about that, huh? So I don't know, man. Let's just do it. I don't have my buddies here. I decided to go back to just the handheld phone and the hand and the paper, because I felt like I rewatched some of the chapter 2 stuff and it felt different, like I had lost something when I switched to screen recording off the laptop. And I'm not sure exactly how much my buddies added to the learning experience. If you've got an opinion, yell it at me in the comments. I will read it. But for now, let's do some analysis, huh? So we're going to get started on chapter 3 of the Cummings Real Analysis textbook. This one's all about sequences. So I guess the first question we should answer is, what the heck are those? Well, a sequence, you might think intuitively, is just a list of numbers. All right, so maybe like 1, 2, 3, 5, 11, 5 again, maybe 64, yada yada. If this goes on forever, we can say that that's a sequence. That's really the thing we need to get down here, is that this thing goes on forever. So a sequence is a list of numbers that looks like that. Good thing is, we don't need a new definition for more formally describing what these things are, because we already have functions. So we can just say that a sequence is a function that takes in a natural number and spits out a real number. So maybe like a of 1 is, if we're talking this thing looks like a function now, this would mean a of 1 is 1, a of 2 is 2, a of 3 is 3. Sort of by coincidence, I guess these happen to line up. But then a of 4 would be 5, a of 5 would be 11, a of 6 would be 5, and a of 7 would be 64. And these can be any numbers. It could then go on. A of 8 is e to the root 2. It could then go on. A to the 9 is, I don't know, what's a real number? Pi squared over 6. And then it could go, maybe a of 10 is the sum of 1 over k cubed, from k equals 1 to infinity. That's a real number. We don't know really much about it, but it's a real number, and there's no reason any of these outputs should be constricted to any kind of number. These are all just real numbers. And typically we'll write AN rather than A evaluated and to save ink. So maybe A1 is 1, A6 is 5, A9 is pi squared over 6, stuff like that. And just because it saves 2 strokes from the parentheses here, saves ink. Mathematicians, we like saving ink. It's what we do. We abuse notation and save ink. If you can do those 2 things, you can be a mathematician. There are a few ways we can define a particular sequence. So maybe this thing isn't particularly easy to define because it doesn't look like it has very nice behavior. But for sequences that are easy to define because they do have nice behavior, we can write out maybe a formula for them. So we can write out maybe AN is equal to N squared. Right, that'll give us the sequence A1 is 1, A2 is 2 squared, which is 4, A3 is 3 squared, which is 9, yada yada. We can define a function recursively, maybe by A1 is, 2, and we can say AN is equal to AN minus 1 squared for any n bigger than 1. So this will give us A2 should be A1 squared, which is going to be 2 squared, which is 4. A3 is going to be A2 squared, which is going to be 4 squared, which is 16, and so on. Or we could write out the first few terms and trust the audience to pick up the pattern. So maybe if I write out 1, 1, 2, 3, 5, 8, 13, you'll say, well, maybe this is the Fibonacci numbers and the next one that comes after is supposed to be 21. So there are a few ways we can denote, or we can define a particular sequence that we want to write in sort of a more compact way. Got these few ways. Sequences can exhibit nice behavior. One of those behaviors is called boundedness. Cummings in his book introduces first a different definition of boundedness, but it's equivalent to this one, so this is the one we're going to use. So we say a sequence is bounded, shortened to BDD. Again, that's more of that ink saving. If and only if there is some C greater than 0, so C here is a real number, where for any term in the sequence, the absolute value of that term is smaller than C. And this could be less than or equal to or less than, doesn't matter, same thing. Okay, this means that the terms are always trapped in a big bubble around 0. So if I imagine I have my real number line like this, I have 0 right here, and I draw a circle around it with radius C. All the terms are inside this circle. Also call that a bubble, also call that a ball, big bubble or ball. Sometimes you call this a ball centered at 0 because it's round, I guess. So if there is a C big enough, and there's no constraint on how big C can be. C can be as big as you want as long as it's smaller than infinity. C can be any finite real number. As long as there exists a C such that this is true, then this sequence is bounded. And we're going to do an example right away showing that the sequence AN defined by this bad boy is bounded. Okay, this is just one of the ways to notate that this thing in here is a sequence because there's an AN for every n from 1 to infinity. It's just what that means. We're going to show that this bad boy is bounded. Well, that's bounded. How can I tell? If and only if there is some c greater than 0 such that for any n, a n is less than c or equal to. Doesn't matter. Okay. So what does this sequence actually look like? -1 to the n over n. Well, if I have my real number line in here, and I have 0 right there, this is 0. Well, a1 is going to be -1 to the 1 over 1, so that's going to be -1. a2 is going to be -1 squared over 2, so that's going to be 1 over 2. Ugh. And then we're going to keep alternating back and forth like this. -1/3, a fourth, a fifth, a sixth. Pretend that's all to scale. So it's going to keep bouncing back and forth like this and getting closer and closer to 0. So how about take c equals 1. So I have my little c here. Boom. That's at -1. Pretend 1 is right here. This is really not to scale. Pretend 1 is right there. Take c equals 1. Then for any n, magnitude an is going to be magnitude -1 to the n over n, which is just going to be 1 over n. And that's going to be less than or equal to 1 because n is at least 1. So there you go. We found a c that bounds all these terms. And that means the sequence is bounded. Hooray. Okay. I think I have... yeah, this page. We can denote sequences in a few ways. We saw in the previous example, I used this sort of notation to say that the thing in here is a sequence. We can do this same thing with parentheses. We can do the parentheses thing just without the n equals 1 to infinity, or we can write out the first few terms. This is how we denote a sequence. Like we're referencing one that already exists, not trying to define a new one. And I like all of these except for 4. I'll use any of these, just not 4. If I ever use anything that's not one of these 3, I don't know, something's wrong. Call somebody. All right. We have some exercises here. Write the first 5 terms of the sequence, this guy, defined by an is 2 to the n. Okay, well, the first 5 terms are going to be a1, a2, a3, a4, and a5. a1 is 2 to the 1 by definition, which is 2. a2 is 2 to the 2 by definition, which is going to be 4. a3 is 2 to the 3, which is 8. a4 is 2 to the 4, which is 16. And a5 is 2 to the 5, which is 32. Now, as a fun exercise, tell me whether this is bounded or not. Moving on, write the first 4 terms of the sequence defined by this. a1 is a2 is 1, so a1, a2. We want all the way up to a4. We know that a1 is equal to 1, and so is a2, right? Because a1 is a2 is 1. And an is the sum of the previous 2. So a3 is going to be 1 plus 1, which is 2. a4 is going to be 1 plus 2, which is 3. And in fact, a5 is going to be 2 plus 3, which is 5. Maybe you see the Fibonacci pattern emerging at this point. That's how you define the Fibonacci sequence. Recursively, is it's the first 2 are 1. Any term that's not one of those is the sum of the previous 2. Cool examples. All right. Convergence. This is the definition. This is analysis right here. The convergence, this is what you gotta have. You gotta learn this. This is important. So maybe watch this section a few times over until you really grok it. Okay. Okay. So a sequence, just some sequence, an for n equals 1 to infinity, converges to a, should underline that maybe. A sequence has to converge to a number that's real. Okay, and that's if and only if, this is the definition, we say that this thing converges to a, if and only if, for any epsilon greater than 0, there is some natural number n, such that for any little n bigger than big N, the distance between the nth term of the sequence and a is smaller than epsilon. Okay, so what exactly does all that mean? Well, intuitively, you can think of it in a few ways. It means the terms of the sequence get arbitrarily close to a and stay there. It means the terms get epsilon close to a for any epsilon. So this is to a. Or you can think of it as for any distance epsilon, no matter how small, eventually every term is in the epsilon bubble of a. So maybe if I have my picture right here, can draw a picture. Here's a real number line, here's some a, here's a bunch of terms in the sequence. Boop, 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 boop. So I have this epsilon right here. I call this the 0th epsilon. If eventually all of my terms end up within this bubble, that's a good sign. I'll draw another bubble, epsilon 1. If eventually all of my terms end up in this epsilon bubble, then we're also fine. Can draw a smaller bubble, yada, yada, yada. If no matter what size bubble I try to draw, eventually all the terms end up in that bubble, then we say the sequence converges to the center of that bubble. And the linchpin here is for any size bubble I draw. There can't be any size bubble I draw where no matter how far I go along, eventually one of the terms leaves the bubble. So no matter what size bubble I try to draw around A, eventually all the terms end up inside there. So let's try an example. You want to show that the sequence an defined by an is 1 over n converges to 0. Okay, what does that mean? We want for any epsilon greater than 0, there is some n in n, such that for any n bigger than n, 1 over n minus 0 is smaller than epsilon. Okay. For this to be true, well, 1 over n minus 0 is 1 over n. This thing is positive, so it's just the same as 1 over n. Well, that's the same as multiply both sides of this by n and divide both sides by epsilon. 1 over epsilon is smaller than n. Now we know, let epsilon greater than 0, by the Archimedean property, we know there is a natural number big enough such that n is bigger than 1 over epsilon. Okay, then for any n bigger than n, 1 over n is going to be smaller than epsilon. Because 1 over epsilon is smaller than n, which is smaller than the little n, because n is bigger than big N. Then, for any n bigger than n, 1 over n minus 0, absolute value, which is equal to 1 over n, is going to be smaller than epsilon. And that's it. So what we actually showed is, what you do is you let an arbitrary epsilon be greater than 0, and then you show that this thing has a corresponding capital N. Since this is completely arbitrary, any epsilon you could have picked has a corresponding N. And that means, good job. You showed what we want to show. So 1 over N looks like this. And you get closer and closer and closer and get to 0. And so we just picked some arbitrary epsilon greater than 0. Maybe it looks like this. And we said there's an N big enough so that all of these terms stay within this bubble, because all these terms are right here. This is the N big enough, such that 1 over N is then smaller than epsilon. All right, so no matter how small we choose this epsilon, we can always pick an N big enough such that all the terms after this big N stay within this epsilon bubble, and that's convergence. Okay, I think I'm gonna end it there. I got stuck in this trap for a long time about thinking that I had to make all of the primer material in one video, and that meant I had to record it all in one sitting. That's just not true, though. I have free will. So what I'm going to do is I'm going to just record, this was about 20 minutes, seems good enough for me, of just the first few basic concepts of the primer material. There's probably going to be 2 or 3 more short videos like this going over what happens in chapter 3. And then we're going to get into some exercises. So look forward to that, I guess. That's all I have. See you next time.